So last time we talked about the energy equation, possibly the most important equation for this class, the equation that we're going to be using the most. We showed how we could derive the energy equation from the momentum equation by assuming steady state conditions and then integrating from some upstream point to some downstream point. So the energy equation is essentially just an integrated form of the momentum equation. And then we did a few example problems involving the energy equation in which we could compute the different hydraulic states, so pressures, elevations, and flow velocities using the energy equation. We moved on to the Darcy-Weisbach equation. So can anyone remind me what the Darcy-Weisbach equation is used for primarily? What is the Darcy-Weisbach equation used for? Yes. Exactly right. So the Darcy-Weisbach equation is one of our primary models for computing frictional head losses. When we're analyzing hydraulic systems using the energy equation, we often need to compute these frictional losses. So the Darcy-Weisbach equation is given by the following general form. We have that the head loss is equal to some friction factor F times the length of the pipe divided by the diameter of the pipe times the velocity squared divided by 2 times the acceleration due to gravity. So we showed how we could use this Darcy-Weisbach model to compute the head losses. But often we need a way of finding this friction factor. So we developed a method to compute that friction factor using the Colebrook-White model. So this is an empirical equation, semi-empirical, designed to compute this friction factor. It's given by the following equation. 0 is equal to 1 over the square root of the friction factor plus 2 log 10 of quantity E over D, where E is the roughness height, D is the diameter of the pipe. E over D divided by 3.7 plus 2.51 divided by the Reynolds number times the square root of the friction factor. So we have a method for computing the head losses, which depends on some friction factor, and we have a method for computing the friction factor based on the pipe properties. But what's one problem that we noticed with this Colebrook-White equation? Yes. That wasn't a raised hand, never mind. What was one problem? Yes. You can't solve for F in closed form, right? So we need to solve this equation iteratively. And last time in class, I showed how we could solve for that friction factor using the solver function in Excel. So we did an example problem at the end of class yesterday. So let's just quickly recap. We have a 4-meter diameter riveted steel pipe in best condition carrying 100 cubic meters per second of discharge, and our job was to find the friction factor F. So we needed some information about the system to solve this problem. We found that the roughness height, E, so this is the roughness height, we looked this value up in our table. Can be found under Canvas pages reference. And we found the roughness height was about 0.9 millimeters for riveted steel in best condition. Corresponds to about 0.9 times 10 to the negative third meters. We had to specify, what is this value here? What does mu stand for in this class? Viscosity. So this is the dynamic viscosity. And we found the value for dynamic viscosity for our temperature conditions. So this was under normal conditions of 20.2 degrees Celsius, 716 milligrams of mercury ambient pressure. And our dynamic viscosity was 1 times 10 to the negative third Newton seconds per meter squared. And our diameter is 4 meters. So using this information, we were able to set up an Excel spreadsheet. By the way, I have a completed version of this Excel spreadsheet under lecture 4, Colebrook-White example 1 completed. So you can download that if you weren't able to successfully run it in class yesterday. And you should get something that looks like this. So we have our parameters here up in column B. So let me just move this toolbar here. Okay. 1 second here. Nope. Okay, there we go. Okay. So we have our parameter values up in column B. So those are all the parameters of the problem. We computed a few quantities for convenience. So we have E over D, that's the roughness height divided by the diameter. That is computed by this formula, B6 divided by B3. So that would be this cell, B6, divided by this cell, B3. We computed the cross-sectional area using our formula for the area of a circle. We computed our velocity by dividing the discharge by the cross-sectional area, and then we computed the Reynolds number. Then we had 2 cells that we are using to try to determine the value of the friction factor. So this cell here, cell C2, this contains the variable that we are trying to solve for. So I'm going to go ahead and reset this. I'm going to set it to 0.1. And then we have our objective function cell. This is the cell containing the Colebrook-White equation. And we are trying to find the value of the friction factor F such that this cell evaluates to 0. So this is the formula that should be in that cell. To do that, we use the solver functionality. So I went to data, solver. I set objective to cell D2, so that's containing our objective function that we want to go to 0. We're trying to set it to a value of 0 by changing variable cell C2. So that is our decision variable, C2. That's the going to contain the friction factor that we're computing. And then I set a constraint here to make sure that the friction factor doesn't become 0 or negative. Now, I know that there were some people in class for whom the solver did not respect that constraint. And so I'll show you kind of a hack I posted in the announcements to get around that. But after filling in our solver parameters, I hit solve. And you should see that the value of our objective function goes down close to 0. So we want this cell to be as close to 0 as possible. And the cell containing the variable we are trying to solve for, the friction factor, starts to converge to the true friction factor that solves this system of equations. So if we want to, we can run the solver again, and the value of our objective function should go even lower. So see, our objective function went even lower, and our value for the friction factor got closer to the true value. So we can continue running it until it stops improving if we want to get more accuracy. Are there any questions on setting up this Excel spreadsheet? Who was able to successfully run this on their own in class yesterday? Can you raise your hands high? Okay, who was not able to successfully run this? Okay, so let's take a moment. I'm going to give you the next 5 or 2 or 3 minutes to try running this Excel workbook. Okay, so I have a fix. So for some computers, for some reason, the solver doesn't respect the constraints that we give it. So to fix that issue, basically we need to modify this formula here to make sure that that value for C2 that's going in for the friction factor can't ever be negative or 0. So to do that, we can take this value here, F, and I'm going to modify it slightly. So I'm going to say, take the maximum of F and 0 point some small number. So I'll say 1 times 10 to the negative 5th. So right now, because F is greater than 1 times 10 to the negative 5th, it's displaying 0.1. If I made this -1, it'll be 1 times 10 to the negative 5th. If I make it 0, it'll be 1 times 10 to the negative fifth. So basically, this just safeguards that variable from becoming 0 or negative. So I'm going to go back into this equation here. Instead of C2, I'll put in C3. Okay, and that should prevent this issue with the convergence that some of you are having. So this cell here, I just made it into max of f and then some very small number, just to ensure that it never goes negative or never becomes 0. Okay, any questions on this step? So some of you may need this to get this particular problem to converge. I'll give you a minute or so to implement this, and then I'll come around to help as needed. But after this, we'll be working through some more examples in class, so we'll have time to practice this. Yeah, so I'll give you a minute or so to implement this change, and I'll come around to help. Just flag me down if you have questions, okay? All right, so in the interest of time, I am going to move on. So I have the completed Excel sheet with the solution for this problem posted, so you can always reference that solution. So we showed how we could use the solver to solve for implicit equations. So to solve the variable that satisfies an implicit equation. Next, we are going to do a slightly more complicated problem in which we have a system of equations that we need to solve simultaneously. So you'll find that this is going to be a pretty common case in this class. And this one can be a bit tricky, so I want you to follow along carefully. So I'm going to do an example first, and then I'm going to have you do an in-class exercise on your own. So let's go ahead and set up our problem. So we have two sections. We have 2 points along a pipe. So let's say 2 sections, A and B, are 4.5 kilometers apart along a 4-meter diameter riveted steel pipe, same as in the last problem, in best condition. So point A is 100 meters higher than point B. If the water temperature is 20.2 degrees Celsius, and the pressure heads at A and B are measured to be 8.3 meters and 76.7 meters, respectively. What is the flow rate? This is a pretty common type of problem that you will need to solve in hydraulics. Let's just make a quick drawing to contextualize here. So we have a pipe. We have points A and B. We have some point A upstream. Oops. And some point B downstream. The pipe is 4 meters in diameter, and that is the same all the way through the pipe. We have that A is 100 meters higher than B. So the elevation change between A and B is 100 meters. We have that the measured pressure head at A, that's PA over gamma, is equal to 8.3 meters. And we have that the measured pressure head at B is 76.7 meters. So we have a decrease in the elevation, but an increase in the pressure head. Okay, so we need the roughness height and we need the viscosity. So this is going to be the same as in the last problem. So what was the roughness height of riveted steel pipe in best condition? 0.9 millimeters, very good. So if we divide that by 1,000, we'll get 0.9 times 10 to the negative third meters. Let's keep everything in standard SI units. And the dynamic viscosity, if we look it up in our table, I'm not going to do it just because it'll take time, but this is 1 times 10 to the negative third Newton seconds per meter squared. And the density from the last problem also, same temperature, 998 kilograms per cubic meter. So that is the information that we have. Okay, what equations do you think we are going to need to apply to solve this problem? There's going to be 3 of them that we need. What's one equation you think we're going to need to apply? Energy equation, very good. So we'll need the energy equation. Okay, in the energy equation, we need to compute something that is not directly known. What is that? What term in the energy equation are we not going to have direct access to? Sorry? Flow rate. So that is true. There's another quantity in the energy equation that we won't know directly. Yes? Head loss due to friction. So what could we use to compute the head loss due to friction? What equation can we use? Darcy-Weisbach. So we'll need Darcy-Weisbach. And we'll need another equation. So what term don't we know in Darcy-Weisbach? Friction factor. So we will need which equation? Colebrook-White, very good. So we'll need 3 equations. Let's say we need these 3. So let's go ahead and start solving this. Yes. We will. Once we know the flow rate, though, we'll know velocity from continuity. So I guess implicitly we also need continuity. But it's just, Q is equal to U times A, right?
Also, are you assuming that this is all turbulent flow?
So we can verify that when we go to compute the Reynolds number. So we'll also need the Reynolds number. So we're going to end up using a lot of equations here. These are the 3 main ones. And then in each of these, we'll also have some equations that we'll need to solve the individual terms within these equations. But yes, so we will also need Reynolds number to determine turbulence, and then it's also used in Colebrook-White. Okay, so let's start by doing an energy balance. That's generally a good place to start. So we have that if we apply our energy balance between A and B, we have UA squared over 2G plus PA over gamma plus ZA is equal to UB squared over 2G plus PB over gamma plus ZB. Am I missing anything? Plus the head loss from A to B. And as we mentioned, we can compute that head loss from A to B by applying the Darcy-Weisbach equation. So that's given by F times delta X, the length of the pipe, divided by the diameter, times U squared over 2G. And then also from Colebrook-White, we have 0 is equal to 1 over the square root of the friction factor plus 2 log 10 of quantity roughness height divided by diameter divided by 3.7 plus 2.51 divided by the Reynolds number times the square root of the friction factor. Okay, so we can simplify this problem a little bit. First of all, it's a system that's at steady state. So we know that the discharge at the upstream end has to equal the discharge at the downstream end. We have that the diameter at the upstream end is equal to the diameter at the downstream end. What does that imply? What does that imply about the velocity? Okay, so it implies that the velocity at the upstream end is equal to the velocity at the downstream end, which I'll just call U. So we can go back and edit this equation. So we don't need a UA and a UB. There's just U. How can we simplify the energy equation knowing that fact? Right, we can just subtract from both sides. So this goes away, this goes away. And so our energy equation is given by PA over gamma plus ZA is equal to PB over gamma plus ZB plus our head loss from A to B. So let's rearrange for the head loss. It turns out that we know all of these parameters here. So we actually know what the head loss is. So the head loss from A to B, if we take this equation and we rearrange it, so subtract PB plus ZB from the left-hand side, we'll get quantity PA over gamma plus PB over gamma plus ZA minus ZB. Okay, we know from the problem statement that the pressure head at the upstream end was how many meters? How many meters? 8.3. At the downstream end, it was 76.7. What about ZA minus ZB? Okay, we know that the elevation difference is 100. So ZA minus ZB is 100. And we can explicitly compute the head loss knowing these facts. So the head loss is known and it's equal to 31.6 meters. Okay, so we can know the head loss just by taking pressure and elevation measurements.
Question.
Yes.
How is it, the pressure plus the other, isn't it minus or?
Oh yeah, sorry, that's a mistake. This should be minus. Thanks for catching that. Okay, so we know the head loss. So we can plug that head loss right back into Darcy-Weisbach. So let's take the Darcy-Weisbach equation and rearrange it such that our friction factor is on the left-hand side. So from rearranging Darcy-Weisbach, we have that F is equal to 2 times the acceleration due to gravity times the diameter divided by the length of the pipe delta X divided by U squared, all times the head loss from A to B, which is known. We also have still Colebrook-White. So that's 0 is equal to 1 over the square root of F plus 2 log 10 times quantity E over D divided by 3.7 plus 2.51 divided by the Reynolds number times the square root of the friction factor. Okay, so we have 2 equations remaining. What quantities in these equations are unknown? Reynolds number is unknown because the Reynolds number depends on what other quantity that's unknown? Velocity. So we don't know the velocity. Okay, and what other quantity is unknown? The friction factor. So friction factor is unknown. Okay, so this is one of our unknowns, the friction factor, and our velocity is the other unknown. The Reynolds number can be computed if we have the velocity, so we'll consider the velocity and the friction factor to be our 2 unknowns. So we have 2 equations and 2 unknowns. Can we solve this system? Yes, we can. So next, I'm going to show you how we can solve this system of equations in Excel. If you go to Canvas Files, I've uploaded another starter spreadsheet for you. So if you go to Files, Lecture Notes, Lecture 5, there should be an example called Colebrook-White Example 2 Starter. And it will look something like this. So go ahead and download that Excel spreadsheet. It's going to be similar to the one we had before, but a little bit different. All right, so I have the sheet pulled up here. Let's go ahead and fill in each of these cells together. So I'm going to start with our inputs here. So what is the length of the pipe delta X in meters? What is the length of the pipe in meters? 4,500. The diameter is 4 meters. Acceleration due to gravity is 9.81. Our viscosity, so our dynamic viscosity is 1 times 10 to the negative third. What is our head loss? So this is a known quantity. 31.6, so this is known. The roughness height, we said before, this is 0.9 divided by 1,000 because we want it in meters. Pi, I'll use 3.14159. And the density is 998 kilograms per cubic meter. So those are our known quantities. We also have some computed quantities that are going to make this more convenient. So first, the roughness height divided by the diameter. I can take cell B7 divided by B3. For the cross-sectional area, we have pi times the diameter squared divided by 4. For the velocity, we have, oh, so first, what is our variable we're trying to solve for again? Flow rate. So let's go ahead and change this cell up here. Let's call this Q for the flow rate, and let's set an initial guess of 1 cubic meter per second. So if we do that, we can now compute the velocity. So this is going to be equal to the flow rate, that's cell C2, divided by the cross-sectional area. Okay, for the Reynolds number, this is going to be the diameter times the velocity times the density divided by the dynamic viscosity. I'm going to make a slight change to this so that we can make sure that our solver converges. So pay attention. I'm going to take the diameter times the absolute value of the velocity times the density divided by the viscosity. So the Reynolds number, I'll paste this out to the side. The Reynolds number isn't designed to be negative. So I put an absolute value around the velocity to make sure the Reynolds number doesn't become negative. Yes.
Where did the velocity come from?
So we're solving for the flow rate. So that's going to be our decision variable. I put it in cell C2. The velocity will be the flow rate divided by the area. So I'll paste that out to the side. I was going to wait till I finish this column, but I'll just go ahead and paste them all out to the side. All right, and then I have a final expression here for our friction factor. So this is going to be solved simultaneously with our flow rate. Remember from the equations that we derived, we have that the friction factor is equal to 2 times G times D times the head loss divided by the length of the pipe divided by the velocity squared. So we're going to use this expression here to compute the friction factor, and that's going to get computed iteratively along with the flow rate. Okay, so that's equal to 2 times G times D divided by delta X divided by the velocity squared, so that's B13 squared, all times the head loss, so that's cell B6. And let me know if I made a mistake there, because I kind of lost my focus for a second. So that's 2 times G times D divided by delta X divided by velocity squared, all times the head loss. So that takes care of all of our computed quantities. So next we are going to define our objective function. So for our objective function, I'm going to use our expression for the Colebrook-White equation. And I'm going to want to make that equation go to 0. So again, we're using this second equation here as our objective function. We want it to converge to 0. So let me go ahead and type that in. So we have 0 is equal to 1 Oh, sorry, I don't need the 0 here. This is equal to 1 divided by the square root of our friction factor. That's cell B15. Plus 2 times log 10 of quantity E over D, so that's cell B11, divided by 3.7, plus 2.51, divided by the Reynolds number, divided by the square root of the friction factor. So I'm going to take that formula and I'm going to paste it below so that you can see it. And if all goes well, we should now be able to solve for the discharge that satisfies the system of equations. So I'm going to go to data solver. We are going to set objective to D2, so that's our objective function. We're going to set it to a value of 0 by changing variable cell C2, so that corresponds to the discharge. And I'm just going to try running it, and I'll see what happens. And I converge to the correct answer. So raise your hand if you were able to get a discharge of about 78.54. Okay, most of you here, raise your hand if you did not successfully converge to 78.54. Okay, so I'll give like about a minute or so. I'm going to come around and just assist those. So I have a problem I want you to work on independently. So work together with your partners to solve this. You can find the problem up on Canvas if you go to quizzes. It's in-class Colebrook-White example. I might change the due date of this because we're a little bit behind where I want it to be. But you'll find the problem statement up in-class Colebrook-White example. So I'll write down the problem up on the board, but this also contains the problem statement here. So I want you to compute the discharge capacity Q in cubic meters per second of a 3-meter diameter concrete rough pipe carrying water at 10 degrees Celsius if the allowed head loss is 2 meters per kilometer of pipe. So let me go ahead and write that out on the board. So I want you to compute the discharge capacity of a 3-meter diameter concrete rough pipe carrying water at 10 degrees Celsius if the allowed head loss is 2 meters per every kilometer of pipe. So go ahead and work on this problem together with your partners. Okay, folks, let's regroup just so that I can be sure we're all on the same page. So let's go ahead and at least get started on this problem together. So first, you'll notice that this problem is very similar to the one that we just did. There's a couple differences in the parameters. So what is the roughness height that you should use for this problem? What is our value for E, the roughness height? 0.6 millimeters. So you can find that from the tables under Canvas pages references. So this corresponds to about 0.0006 meters. Okay, what about the dynamic viscosity? 1.307 times 10 to the negative third. And that is in Newton seconds per square meter. What about the density? Okay, the density is 999 kilograms per cubic meter. There's also one other difference in the way that this problem is formulated compared to the previous one. In the previous problem, we gave you the head loss explicitly. In this case, we give you the head loss per unit length. What's an easy way that we can adapt our previous problem template to this problem? We have a head loss per unit length. How can we deal with this new situation here? Yes.
Choose like 1 kilometer as your length.
Yeah, we can just choose an arbitrary length. The easiest thing to do is to just assume that delta x is equal to 1,000 meters. And thus our head loss is equal to 2 meters. So with that, we should be able to just adapt our existing spreadsheet. Everything else will be the same, but we can change our distance to 1,000. We can change the diameter to 3, viscosity to 1.307 times 10 to the negative third. Head loss is now 2 meters per that 1,000 meters. Roughness height is 0.6 divided by 1,000, and density is 999. Everything else should remain the same. I will leave the rest of the problem up to you, but if you run this Excel workbook, you should arrive at the correct discharge. Okay, with that, I will let you go for today.